Good morning, afternoon, and evening, everyone, and welcome to Fike's spring/summer, it's almost here, series of webinars regarding combustible dust. And we're all incredibly stoked to have you with us. We've missed you very much. Today's topic of webinar is the combustible dust hazards and steps to compliance. My name is Carson Stevens, and I am the Explosion Protection Business Development Manager for the Pacific Northwest and for our OEM partners. And we have a very special panel of speakers coming at you from around the world today to discuss this particular topic. And up first to cover what the heck is a combustible dust hazard, we have Mr. Jim Vingerhoots, our Global Explosion Protection Product Manager. Good afternoon to you, Jim, in Belgium, and the floor is yours, sir.
Thank you, Carson. This is the first webinar in a series of 6, which will run until the end of May. And of course, you are invited to any of these. Today, we will start with the dangers of dust explosions. And it is so that if you are handling, processing, storing, or transporting combustible bulk materials or powders, then you are always at risk of a dust explosion. Materials at risk include pellets, powdered food, animal food, grains, sugar, starch, malt, wood dust, coal, drugs, plastics, chemical dusts, and metal dusts, such as iron, zinc, and aluminum. Processing operations at risk include conveying, storage, drying, milling, mixing, sieving, classifying, and filtration. The hazard arises from the ability of fine dust particles to become intermixed with air at enough concentration and finding a hot spot, spark, or ignition source, with a rapid combustion propagation as a consequence. The speed of combustion is so rapid that you cannot run away when it occurs. And if the combustion happens in a confined space, such as in a dust collector, associated pressures increase and will rupture the collector's casing and endanger nearby personnel with flames, blast waves, and flying metal parts. The finer the dust particles, the more rapid the combustion. Particles larger than 0.5 millimeter can participate in a fire, but burn too slow to sustain an explosion type of combustion. At the top right hand, you see a photo of an ongoing dust explosion happening in a bulk materials handling facility, which expresses the typical scale at which this occurs. The bottom right photo shows a grain storage facility after a dust explosion. Pressures associated with the rapid combustion of grain dust have ruined the structures in which the explosion took place. In the video that we will show right away, you see a real dust explosion. 2 pressurized bottles with cornstarch are installed opposite each other and released simultaneously. A copper wire in between the bottles is heated electrically. As soon as the cornstarch reaches the hot wire, the dust cloud ignites. Combustion propagates rapidly from the middle away to left and right with a speed of several meters per second. Statistics show that dust explosions keep on occurring in industry. The Canadian Dust Safety Science has recorded 51 dust fires and 28 dust explosions in the first half year of 2021. This is just the top of the iceberg. It is known that most incidents are not reported or made aware of to the public. While the likelihood of being involved in a fire is for sure larger than being involved in a dust explosion, the chance for injuries and fatalities is far higher with dust explosions. Also, a dust explosion can follow a fire, and often a fire follows a dust explosion. The statistics also reveal which combustible powder handling industries are most involved. Number 1 is agricultural and food processing. Number 2, wood processing. Equipment most often involved are storage silos, dust collectors, dryers, and bucket elevators. To understand the hazard of a dust explosion better, let us look at the chemistry and physics that play. As said before, a dust explosion is a rapid combustion of fine dust particles dispersed in air. It is similar to a gas explosion, but gaseous fuel is now replaced by particulate solids fuel. Although small solid particles burn slower than gaseous fuel because they first need to evaporate, they also increase the combustion speed because the particles move in the air and drag combustion flame from one location to another. The combustion reaction itself is identical to any other fire type of combustion, just faster. Fuel and oxygen react and produce carbon dioxide, water vapor, and heat. If the explosion happens in a confined space, such as inside process equipment, the combustion gases produced, as well as the temperature rise due to the liberated heat, will increase the pressure. When an ideal mixture is met, where exactly all available oxygen in air and dust particles is burned, the temperature will rise to about 1500 to 2000 degrees C and pressures to 8 to 10 bar. The explosibility of dust depends on many factors, such as chemical composition, particle size and shape, moisture content, dust concentration, and turbulence level in air. It is good practice to let your dust tested in a lab to quantify the hazard it poses. This can be done in a so-called 20-liter sphere, which is equipped with a dust dispersion system, igniter, and pressure transducers. The pressure recordings reveal the maximum pressure, Pmax, and the maximum rate of pressure rise, the PDT max. Since the maximum rate of pressure rise is inverse proportional to 1/3 of the volume in which the explosion takes place, the speed of combustion is often expressed by the volume normalized value of the maximum rate of pressure rise, the so-called dust explosion constant, or KST. The hazard of combustible dust explosions is not only expressed by the effects it can cause, but also by how easily the explosion can be initiated through a so-called ignition source. The most frequent occurring ignition sources in industry are mechanical sparks, followed by static electricity and hot surfaces. Also, exposure of a dust cloud to direct fire or welding flame is found to be the cause of the explosion, as well as self-ignition and smoldering. Malfunctioning electrical equipment can also initiate the explosion. The ignition sensitivity of dust clouds and dust layers can also be measured in a lab, and the results can be quantified, such as the minimum ignition energy of a spark and the minimum ignition temperature of a hot surface. Enclosed table shows some typical values of selected dust hazard parameters measured in a test lab. The maximum generated pressure, Pmax, varies from 8 to 10 bar for organic dusts, but can be much higher for metallic dusts. Also, the dust explosion constant KST can quite differ per dust type. Minimum ignition energies typically range from 5 millijoule to 1 joule, and the minimum temperature for a hot surface to ignite the dust layer is typically in the order of 300 to 500 degrees C. Unless otherwise stated, a lab will report the explosibility parameters for a worst-case situation. That means the dust samples sent in will be dried and sieved to withhold the finest fraction before testing. Testing will happen at a range of dust concentrations in air, and the worst case will be reported. For organic dusts, the explosibility range is typically between 50 to 3000 grams per cubic meter dust dispersed in air. To give you an indication how much this is, a light bulb of 25 watts can hardly be seen from 2-meter distance through a cloud of 50 grams dust in 1 cubic meter air. Combustible dust clouds will typically be produced during regular processing operations, such as filling of a storage silo, cleaning of filter bags in a dust collector, conveying bulk products with a bucket elevator. But also dust layers just lying on the floor are a potential hazard. Imagine a plate falls on the ground with dust layers. The dust will whirl up and can form an explosive dust cloud. If a motor is placed in the vicinity and has a hot surface, a combustion chain reaction may follow. It can easily be calculated that a dust layer of only 1 millimeter of product can fill a room of 5 meters high with a dust cloud of 100 grams per cubic meter. Therefore, dust layers should never be allowed in factories, and dust cleaning operations are crucial for explosion safety. Dust layers and accumulations can also be involved in secondary explosions. Imagine a powder processing equipment is involved in an internal dust explosion. The explosion pressure rises and ruptures the casing of the equipment. A fireball and blast wave is ejected out of the ruptured equipment. Dust accumulations on shelves and floors in the vicinity are whirled up by the blast wave. Dust clouds are formed and sustain the combustion. With a bit of bad luck, when the factory is not cleaned from dust layers, the complete factory is involved in the dust explosion and a catastrophic event takes place. Explosions can not only propagate in a factory through whirled up dust layers, they can also propagate from one processing equipment to another through interconnected pipelines. We will show you videos of dust explosions executed on the Fike remote test site that demonstrate this phenomenon. Wood dust is dispersed in a 5 cubic meter vessel and ignited. The vessel is fitted with explosion vent panels to prevent it from uncontrolled rupture. 16-inch pipelines of 10 meters long are connected to this vessel, and a blower makes sure air flows through the system prior to ignition. As you can see, following the dust explosion in the vessel, dust and flame is reversed out of the vessel due to the explosion overpressure and propagates totally to the end of the pipelines. Even with clean pipes at the start of the explosion, enough unburned dust is ejected out of the vessel into the pipelines to sustain combustion for several tens of meters. Blowers are typically not able to push back dust explosion flames. Explosion mitigation measures should therefore not only protect process equipment vessels, but also their interconnections. If the connections between the process equipment vessels are not protected, explosions can propagate from one process vessel to another. This not only increases the scale of the dust explosion, it also makes the situation more and more unprotectable. A dust explosion experiment carried out with a 1 cubic meter and a 5 cubic meter test vessel showed the maximum pressures and the maximum rates of pressure rise were considerably increased when both vessels were interconnected and the explosion was allowed to propagate from one vessel into another, compared to the situation where both vessels were involved in isolated explosions. Rates of pressure rise increased with factor 20. Now that we gave you an overview of the different explosion hazards that are constituted by combustible dusts, it is time to start thinking of steps to take to protect against the hazards. Normally 4 steps are taken. Test the dust to see if it is explosive, how sensitive to ignition, and how severe when it explodes. Where in the factory is the dust? Where are the potential ignition sources? Remove sources of dust, eliminate ignition sources, and apply mitigation measures in case the dust explosion would still occur. With this, I give the word back to Carson, who will introduce the next speakers who will elaborate on protection steps, regulations, and the road to compliance.
Thanks, Jim. Gotta say, again, thoroughly impressed that you're able to get that all in the short amount of time that we have. That's literally the smallest little bitty tip of the iceberg. but thank you. Before we go any further, I forgot to mention at the beginning of the webinar that we're saving some time at the end of our webinar for some questions for our experts on the panel. So if you have any questions in the meantime, if anything pops up in your head, just throw it in the chat, and then we'll get those answered to the best of our ability with the time that we have at the end. So boiling it down, what Jim's saying is that essentially if there is an enclosure and you have a combustible dust within that enclosure, there's a chance for a cloud, there's a chance for an ignition source, and you have a combustible dust hazard. That's not a local or a regional problem, that is a global problem. That's an everywhere situation. So if I'm mitigating a combustible dust hazard in Blue Springs, it's probably going to be a little bit different than if I were to be mitigating it in, say, Herentals, Belgium, for example. To run through some of the relevant codes and compliance for a dust hazard in the US, and I don't want to embarrass him, but he is the godfather of Fike explosion protection. He's been on Fike for nearly 50 years, not kidding. Real deal. It's Mr. Bruce McClellan. Good morning, Bruce. How are you this morning?
Good morning, Carson. Thank you so much for that nice introduction. Really looking forward to spending a bit of time here with our audience today. Jim, I want to tell you it was great information you gave us. Thank you so much for doing so. But we're going to talk a bit today about regulations for dust safety and about regulators and how they fit into the big overall picture for explosion protection and dust concerns. Jim had done a great job of identifying the risk, and following me will be Dimitri, who is going to talk about things more specific to the European community. So I'll focus mostly on the United States, as Carson was saying. Combustible dust regulations generally fall into one or two categories. They're either directed toward operating a safe plant or facility, or directed toward operating equipment safely in the workplace. In either situation, the regulations are directed toward the facility owner and or their assigned operator. Both categories also have a focus on the safety and well-being of the workers, visitors, contractors, or generally the human element at the location. Regulations regarding a safe plant have a focus on dust exposure throughout the buildings, providing direction on fugitive dust or dust accumulations that may pose a threat to the personnel as well as the building or structure itself. Regulations such as NFPA 101 Life Safety Code, NFPA 70 National Electric Code are two examples of such regulations. Further regulations regarding the safe plant can be specific to the type of dust and or to the industry the dust belongs to. Specific details of recommended practices such as dust layer depth allowable accumulations, cleaning frequencies, use of zone separation, or building segregation give confidence that if an event were to occur, the magnitude of the catastrophe would be limited. Recommendations on the limiting of an ignition source are identified, and specifications as to the ongoing management of these hazards is spelled out. Guidance is also specified as to when and where explosion hazard may continue to exist in a building. Explosion venting of the room space shall be provided to limit facility structural damage. Safe plant regulations strive to instill operational practices to ultimately eliminate or minimize the consequences of a secondary explosion at the facility, should one occur, by limiting structural damage, reducing the available combustible dust that can become engaged in an event, and provide instruction as to a plan or action should such an event occur. Regulations regarding safe equipment are also directed at prevention of a combustible dust explosion or fire, and where that is not always possible, how to minimize any exposures to personnel and damages to the operating equipment are identified. The very nature of the equipment in these facilities most often sets up the condition to encounter a fire or explosion. Safe equipment regulations focus on these events, typically smaller in scale than the whole facility or secondary explosions. Prevention of an explosion, as well as protection or mitigation of an explosion, should one happen, will provide protection for the personnel, as well as limiting the magnitude of the loss. One regulator familiar throughout industry is OSHA, Occupational Safety and Health Association. OSHA is one of the regulators that can write rules, enforce rules, conduct facility audits of worker conditions, write findings, issue penalties, levy fines, and if deemed appropriate, cause facilities to discontinue operation. OSHA's role regarding combustible dust is primarily focused on personnel safety and therefore may have findings on both the plant, facility conditions, and the operating equipment used in the production of combustible dust at the facility. OSHA is one of the regulators that over the past decade has become very active regarding combustible dust. In a moment, we'll dive a bit further into their actions, but to bring about a more safe and secure environment in the workplace handling combustible dust. Other authorities having jurisdiction over facilities are represented by delegates of local government. These authorities may perform worksite visits to inspect, evaluate, and qualify or clear the facility of hazardous situations. Among others, any fire marshal of a governmental branch is permitted to examine a facility and/or equipment conditions and operational function to determine if a hazard exists and enforce actions to remedy a dangerous condition. Often, it is a situation that a facility does not know who at their specific site would be an authority having jurisdiction regarding fire explosion. Understandably, facilities may be hesitant to inquire as to who or what entity would have these authorities, but it would be much better for the owner-operator to make inquiry and discovery as to which authorities may be in place, and thereby express an eagerness to operate with a worker-safe and equipment-safe facility. Other authorities exist and often publish standards or even codes with best practices in accordance with current knowledge and industry advancements. Two such organizations that are well known throughout the globe are the VDI, which Dimitri will discuss, and the NFPA, which I'll cover a bit further in this presentation. It is a regular practice that local authorities will require for individual components used in the construction of a more complex process or operating building, where combustible dust is present, to have a validation of suitability for use in that particular environment. Electrical fixtures, for example, will be required to be marked as validated for use in a specific environment. Underwriters Laboratory is one such organization performing component equipment examinations. Often in combustible dust handling facilities, the individual component must meet electrical classification criteria to be considered explosion rated. These ratings often identify the component as being suitable for areas such as Class 1, Class 2, or Division 1 or Division 2, and groups A, B, C, groups E, F, G, depending on the component's application requirement and suitability. Insurers may impose additional or alternative requirements, varying with their particular loss history, technical expertise, and risk tolerance. FM Global, for example, has developed a series of data sheets which guide the insurer's risk auditors in making recommendation of exposures, safe handling, and processing practice recommendations. Operation and combustible specific safety measure are identified in these specific data sheets. Most often, however, insurers or reinsurers adhere more to the safe practices identified in the NFPA combustible dust standards and codes regarding facilities and equipment. An additional point for facility owners, operators to consider relating to insurers' recommendations and findings should be considered. While facility, equipment, and business interruption insurers may care deeply regarding the human element at work in the facility, most often the insurance being offered is in relation to the building, equipment, and continuous operation of the insured's deductible. The absence of an insurer recommendation to enhance the safety in the facility regarding the worker or employee safety does not typically indicate the facility is or is not operating in compliance with a national standard such as NFPA. OSHA is the primary, highly organized agency positioned to administer enforcement of combustible dust standards. OSHA is charged with a great many responsibilities regarding the well-being and safety of America's workforce. Being established and overseen by Congress within the U.S. Department of Labor, OSHA's administrator answers to the Secretary of Labor, who is appointed by the President of the United States. OSHA does have a national office located in Washington, with multiple field offices separated into regional and area offices. Regarding the state's offices of OSHA, nearly half fall under the jurisdiction of the federal OSHA, and the other half are under the jurisdiction of the individual states. In reference to combustible dust, a single standard was created by OSHA. This standard, drafted decades ago, was in relation to a series of incidents in the grain industry. Once created, this standard was brought to bear by enforcement with a specific focus on grain operations. No updates or additions have since been adopted by OSHA. In the early 2000s, it was again identified that an increasing number of combustible dust incidents were occurring in industry. In response, OSHA created a combustible dust national emphasis program to help industry recognize and work toward a higher level of worker safety. Shortly after this new program, a major combustible dust loss event occurred in 2008. OSHA renewed this national emphasis program and began a significant education, instruction, and investigation program. This program continues today and leading the way to improved worker and employee safety in all industries. In consideration of OSHA's limited combustible dust standards, their area, regional, state, federal offices have used the General Duty Clause as a means to assist owners and operators to continue their move towards improved safety in the workplace. If an owner or operator is permitting for new construction, they will likely encounter the need to submit plans for the use and constructions to local regulators. In most cases, that regulator will be at the state level or under. In some situation, a federal level may be required, depending on the facility and or property manager. Plan review when considering a combustible dust facility equipment use should include the involvement of a fire marshal. There will be considerable variation of what is required based on location of the work, geography of the facility, knowledge, training, education of the authorities in charge. There is little consistency between authorities as to what combustible dust regulations will apply, and even to the point of no known requirements. It should be expected and welcome that other authorities will be involved and offer persuasion as to what other considerations are in place or should be further pursued. Insurers can lend a hand to identify their minimum requirements, as well as possibly identifying other specific codes such as NFPA that they may recommend. Corporate directives from large employers are often enacted to facilitate worker safety and asset protection. Corporate standards should be enacted to facilitate consistency across various plant sites and operational processes. Consistency in operational steps, practices, reporting, emergency response protocol, record keeping, etc. Being standardized within a corporate entity will result in a safer workplace and also operational efficiencies. The International Building Code is a collaboration of experts with vast education, knowledge, and experience in the practice of quality construction with safe usage for the occupants. It is with great purpose the states of the United States have adopted the International Building Code as a model for the minimum requirements of new and existing building structures. International Building Code recognizes combustible dust as a serious threat to the occupants, workers, as well as the construction of the building and structure itself. This code directs that it be to the owner's responsibility for compliance to provision for fire and explosion of combustible dust construction standards. The International Building Code explicitly points the owners or their assigns to the provisions of the International Fire Code and the National Fire Protection Association standards, including NFPA 652. Not following these globally recognized practices will put the owners and their assigned parties directly in the line of responsibility when accidents and/or combustible dust events occur. The International Fire Code is a model code regulating the minimum fire safety requirements for new and existing buildings, facilities, storage, and process. The International Fire Code provides a total approach of controlling hazards in all buildings and sites, regardless of the hazard being indoors or outside. It should be part of your review plan as you're looking for any new construction or evaluating your existing facility. As we share discussion as to who are and what is the regulations that are to be met, a consistent message has been delivered. That is, regulators are most often using the NFPA standards as a basis of what should be done and how to manage combustible dust, fire, and explosion hazards. NFPA combustible dust standards are recognized as the most comprehensive regulations for workplace safety and property preservation when it comes to operations and mitigation. The combustible dust standards of NFPA are written primarily by industry volunteers who have a purpose to provide a safe and productive workplace environment. These experts have deemed the criteria and the standards to be the minimum acceptable industry practices for safety in the associated industry. The standards are reviewed extensively, voted on, and then adopted by NFPA community at large. National Fire Protection Association is made up of codes and standards. Often the term are used synonymous, but there is a slight difference. Code is a standard that is extensive and covers a broad subject and is suitable for adoption in law on its own. Standard is the main text containing only mandatory provisions, such as by using shall in a form suitable for reference by another code or standard. Presently, several of the numerous NFPA combustible dust standards are being compiled into a reconfigured document that is being referred to as NFPA 660. NFPA 660 on combustible dust is rumored as being a code instead of a standard. An example of this code would be NFPA 70, the National Electric Code. Though I've already touched on these points today, I think they're worthy of an additional mention. NFPA is viewed as the most comprehensive and inclusionary compilation of minimum safety and protective practices as recommended by industry. NFPA is often used by regulators and authorities as a basis of training and education. NFPA is living documents under continuous review and edits as new information and technologies become available. NFPA compliance is to the facility owners and operators' responsibility. Hopefully, you'll never be in a position to defend why you did or didn't do anything industry recognizes as a minimum life safety. But if you are, it will be much better to have NFPA compliance on your side. Beginning with the 2017 edition of NFPA 652, a dust hazard analysis is a requirement for all facilities and all processes with combustible dust. If not already, be sure to have a DHA completed now, as it will provide direction on combustible dust areas in your facility needing immediate attention, as well as those you've already taken care of or you've been concerned with that may actually be in good shape. It's much better to know and to resolve issues than to let them go unnoticed. Hopefully, something in this short presentation provides some information you're wanting or needing to know. This list represents several of the combustible dust standards found in NFPA. If you need help, call an expert. And in closing my section, Carson, I'm handing it back to you.
Thanks, Bruce. Super nice summary. I know you can write a book on this stuff, so I really appreciate your time today, and we all do. So that covers one side of the globe. There is a whole another half of the world that has the same hazard, but maybe a slightly different approach. So to discuss the European approach is our Fike Europe-based explosion protection scientist, Dr. Dimitrios Gakogiannis. Good afternoon, Demi, and thanks for being with us today. I'll turn it over to you.
Thank you, Carson. Thank you for the introduction. Thank you also, Jim and Bruce, for referring to this presentation that I'm going to show to everyone. So I'm going to talk about safety regulations and compliance, but focusing mainly on ethics. What do we do here in Europe, and how plant owners and manufacturers comply to the law for safety. First of all, I'm gonna start with the basic idea behind safety regulations, the basic idea behind ATEX, but this is a very general idea for all safety regulations, and it's something to keep in mind. So 3 words are the magic words: prevention, avoidance, mitigation. PAM are the initials. So step number 1 is the prevention of formation of explosive atmospheres in a place where we have a hazardous substance, as the ones as Jim presented. The second step is to avoid ignition of the explosive atmospheres. In order to have an explosion, by having just a cloud, we need to have an ignition, and this is what is going to create the explosion. And if we cannot work, the first 2 steps do not reduce the possibility to 0, and there is a chance of an explosion, we need to take measures to mitigate these effects. At the bottom of this slide, you can see the risk of having an explosion that is equal to the possibility to have an explosive atmosphere multiplied with the possibility to have an ignition multiplied with the possibility to mitigate the explosion effects. So the risk of an explosion means the risk to have a damage, to risk to have consequences from the explosive atmosphere at the event of an explosion. And you can imagine that if someone reduces any of the 3 possibilities to 0, there is no risk anymore. So the truth is that there is no possibility to reduce any of these 3 possibilities to 0. All these 3 steps keep busy the plant owners. The owners that they have a manufacturing line, and there is the presence of organic dust, metallic dust, whichever is the hazard, or a gaseous mixture, an inflammable gas, for example. And this keeps them busy. They need to take measures. They need to keep the place clean. They need to take measures to avoid, to take action, let's say, to prevent, avoid, or mitigate. These 3 boxes that you see, the tasks that they are described in these 3 boxes, are also tasks that they are undertaken also by the manufacturers of protection equipment. There are devices that they focus on prevention of the formation of atmospheres. There are even devices of avoiding ignition sources, or devices that they mitigate the blast effects. I guess most of us are more familiar with devices that they mitigate the blast effects, but there can be other devices as well. So that's the basic idea behind these regulations. That's the intention, that's the strategy in order to avoid an explosion. And another basic concept which I would like to present and discuss is the, let's say, the bureaucratic part. So first we have a strategy, we have the technical approach to the problem, but then we have to have an administration process that is going to oblige plant owners and manufacturers to align and focus on these three: prevention, avoidance, and mitigation that I described before. So this is done by laws, standards, and harmonized standards. The laws are rules that, if they are not respected, there are penalties. The standards are kind of agreements that they show a kind of intention to comply to the law. They are methods commonly recognized, where when applied in a workplace, they reassure that there is the intention to comply to the law. Harmonized standards, on the other hand, they go within Europe hand by hand with the law, and they are kind of instructions for plant owners and equipment manufacturers in order to help them to comply to the law. And I'm going to explain it in a while. So in Europe, an example of a law is the ATEX directive. The ATEX directive is a law, European law, that is above any other, above the laws of any member state within the European Union. It's split in two parts. In ATEX 153, it is also called 199/92 EC, but I'm going to call it 153. And it's focusing to the workplace, on how we should handle hazards in the workplace. And it's concerning mostly the plant owners. And we have the ATEX 114 that it's aiming to place safe equipment, suitable equipment within a hazardous environment. And here we have some examples of standards. In the European Union, the harmonized standards, they are regulated by the Committee of the European Normalization. There is a technical committee that develops the standards for potentially explosive atmospheres. And these are the harmonized ones. They are ones that they give instructions to manufacturers and plant owners on how they should comply under the ATEX directive. So let's discuss first the ATEX 153. The ATEX 153 requires from the plant owners to have an explosion protection document. Imagine this, it's a kind of report that is describing the hazardous environment, and it classifies the hazards within the workplace. It gives clear instructions on how the plant owners should treat the hazard in the workplace in the various areas. The plant owners should comply with the following basic rules. First, they need to identify the hazardous areas. Here needs to be it needs to be a classification of the hazardous areas, where we can have a higher risk or a lower risk or no risk of an explosion. Second step is to identify and remove ignition sources. So that's the avoidance from the prevention, avoidance, mitigation. Third step is to ensure that dust hazards cannot harm workers or the environment. And the last thing is to test the hazard, to know the intensity of an explosion in case that an event happens, so that we can address the mitigation correctly. So we fall, actually, these 5 steps that they were presented before, they can be summarized again into prevention, avoidance, and mitigation. Prevention of the explosive atmosphere, avoidance of the ignition, mitigation of the blast wave in case of an explosion. As I said, there is a classification of the hazardous areas. You see often this symbol. Within ATEX, we classify the zones in 3 categories, depending on how dangerous they are. So there are certain areas in the factory. Imagine that we're going to have the hazard present more than other areas. These areas, they are tagged like this, and they have to have this sign. So there are three categories, as I said. We have zone 0, 1, and 2, or zone 20, 21, 22. This is for gases and vapors. This is for dusts. In zone 0 or 20 are the most dangerous one, because there we have continuously present a dust cloud or mist. In zone 1, we have a cloud or a mist that is likely to occur, and zone 2 is the safest, let's say, one, the most easygoing. Here is an empirical table that gives a kind of indication of what it means: continuous, likely to occur, or not likely to occur. So zone 0 and 20, we have more than 1 hour per shift, a cloud present, a dust hazard present, a dispersion of a cloud ready to be ignited, or more than 1,000 hours per year. Likely to occur is less than 1 hour per year, but more than 10 hours per year. Likely to occur, a cloud likely to occur is nearby equipment. It's not very close, because there would be a zone 20, but it's nearby. So inside an equipment, we can imagine that we have continuously the presence of a cloud. But once we are 1 meter away, we likely are going to have a cloud present. And not likely to occur is less than 10 hours per year or less than 1 minute per shift. So this is an empirical table commonly used for identifying the possibility to have a cloud there. So we can classify the zones. And let's go now to discuss ATEX 114 for the equipment. So this part of the directive addresses electrical and mechanical equipment. And it applies to all member states, as I said before, for all manufacturers that they want to distribute products within the European Union. What are the obligations of the manufacturers? They need to identify and remove potential ignition sources. The device should not pose a threat, should not be emitting sparks, should not be hot. They should demonstrate by design experimentation with testing that the equipment does not generate ignition sources and that the protective system performs as it's supposed to, according to its design. So these efforts are documented by third-party notified bodies, are called in Europe. So it's a third party that is going to provide the certificate, and it's going to test the equipment. It's going to document everything, mark the equipment. So all devices within the workplace where there is an explosive hazard need to have a marking, and all these papers, they need to accompany the device. And certain papers need to accompany. There are documents that they describe the performance of the product, the proof that it's certified, and needs to be together with the product. So this directive is covering electric and non-electric equipment, mechanical. It's a product directive, and the equipment, the basic idea is that it should not cause an explosion. It should not pose a risk. Here you can see an example of the tagging of the ATEX mark example. So there is a kind of methodology in which everything is described on the tag, on the marking of the product. The products, they need to have this logo on them, similar as the logo that it needs to be placed in the zones, in the ATEX zones. And we have three categories of equipment. Category number 1 is equipment with a very high level of protection. This kind of equipment should be almost impossible, not almost impossible, it should be impossible to cause an explosion. Category number 2 is an equipment with high level of protection, and category 3 is an equipment with a normal level of protection. So this equipment can be anything. You can imagine that it can be protective equipment, it can be radios, it can be anything that will enter within the zones that were described before. These three categories, they're aligned with the zones. And here you can see how it's the whole connection between 8x153 and 8x114. We have the zones, the dangerous one, the less dangerous one, the least dangerous one, with the categories of its equipment. So you can enter in these zones with these products. You can install these products in these zones, or the worker that is carrying these products can enter in these zones. So everybody, in a way, knows what to do, and the rules for plant owners and manufacturers align together. And that's the last slide, concluding on how ATEX works.
Thanks,
Thank you
Timmy.
for your attention.
Appreciate the time. Great job and great summary as always, and really appreciate you putting that together for us. So with the remaining time that we have, I've been taking a look at some of the questions. There's like 30 or 40 questions in here. We're not going to be able to get to all of them, but we're going to do our best in the time that we have. I'm going to try to throw each one of our panelists one within their bailiwick. And then we've also got our slide up showing our upcoming webinar schedule. So if you can jump in any of those too, because those are some interesting topics and things that we heard from you guys what you'd like to hear. So the first one I'll grab, if that's okay with everybody. Is there any type of dust that is not totally combustible, or are they all? Great question. They're not all totally combustible. For example, calcium carbonate is a material that has a super fine powder that's not normally combustible. Of course, that's subjective. It can be combustible if mixed with other combustible materials, but in general, organics such as like agricultural, food, pharmaceutical, plastics, things of that nature, metals, definitely metals are very much combustible. But that's why it's important to get your dust tested. It's a small fraction of knowing. It's better to know up front than not know at all, and it's a pretty small cost comparatively. So get your dust tested. So got a question for Bruce, and it's a good one, I think, for you, Bruce. As fire/explosion standards have become more stringent, many plant operators claim that they do not need to act as their equipment is grandfathered. What is the correct response? Bruce, if you would take that one, please.
Well, it's a great question, Carson. It often comes up because a lot of folks don't want to participate in the, let's say, current safety standards of industry. But by definition, grandfathering is well explained in the NFPA standards. And generally, I'll try to generalize it for you here. If there is a risk to people, then grandfathering is not really included for those particular areas. The numerous different NFPA standards that have been revised, as I mentioned, within the last 3 years and be revised again within the next 3 years into NFPA 660. These all have criteria which states grandfathering does or doesn't apply to certain sections of the NFPA standard which we're referring to. NFPA 61, for example, has its own criteria. And try to summarize it is that if there's a risk to the people, if there's an explosion hazard, then the implementation of a new methodology is still in play. And particularly, dust hazard analysis is in play for all the NFPA standards regarding combustible dust.
Perfect, Bruce. Thank you. Thank you, sir. Got one for Jim. And it's a good one. Where can dust be tested for combustibility? I figured you could talk about the offering there.
Yeah, it can be tested at multiple labs existing around the globe. Fike has a test lab, so you can contact Fike or others. But yeah.
Thank you, Jim. And
Yeah.
then the last one we have for Demi, and it was, I'm trying to find the good one for you because it was based on your talk. So Demi, regarding ATEX, what instruction and training is required for workers and employees?
Everything should be, there should be training of the workers, and everything is described in the explosion protection document. So in relation to that report, the plant owners, they need to give instructions to the workers in order to keep everyone aligned, and everyone needs to know what to do. Everybody needs to be coordinated. So they need to have a kind of training, and there are clear instructions. There should be clear instructions in the explosion protection document.
Thank you, sir. I think we've got time for one more, and I could probably do this one, but I think I want to throw it at Jim and give him a brain buster here. Okay, so how much energy does a mechanical spark have? Is there a threshold when MIE is not affected by a mechanical spark?
Yeah, that is for electric sparks. There is a better knowledge, of course, on what is a static discharge from a human body to another conductor or a propagating brush discharge. These are known. A mechanical spark can be small or large. So it is typically, if you can see it, then it is typically relatively, and then it can be several tens of millijoule. And then that is the order, but it depends on how large this spark is.
Right. Sorry, that was kind of a hard one but yeah, I think what you're saying is it's pretty variable. For our MIE test that we have, anything below 25 millijoules, kind of like the area Jim's kind of talking about, is considered a high sensitivity or a high minimum ignition energy. And then there's various levels going up that make it more difficult to ignite. So the threshold that you're referring to is MIE. It's just, where does the mechanical spark fall within the MIE for your particular dust? So I hope that makes sense, but and I didn't mean to throw you under the bus there, Jim, but so I think that is all the time we have today. So I want to just extend my thanks one more time. All of our thanks, our panelists, everybody that put the webinar series together and everything. Everyone's done a great job. So I really appreciate everyone's time, and we look forward to seeing you perhaps on May 4th. May the 4th be with you. So we'll see you then. Have a great day. Thanks again.